Good morning. Welcome back, my dear students. So, earlier we started with surface chemistry and we completed adsorption and catalysis under surface chemistry. Now I am going to the last topic under surface chemistry is colloids. So, number of the new concept will come. You have to understand very carefully. I will explain one by one. First, what is meant by the term colloids. So the colloids is a word derived from Latin. It is called the colla. Colla means glue. Ides is like. Glue-like compounds are called as the colloids. So the name has been derived Latin name. The colla means glue. Ides is a glue-like compounds known as called the colloids. So actually Thomas Graham was conducting the experiment of diffusion of particles through the parchment membrane or pig's bladder or leather membrane. He did some experiments one by one. He has taken the suspension. Suspension means he has taken the freshly prepared precipitates, he has taken and placed in the parchment membrane, and he was studying the diffusion property. And he found that the particles of these precipitates, I call it suspension, they are not found to be passing through the membrane. They call those they are part of the suspension. So in the beginning, Thomas Graham has taken the freshly prepared precipitates like barium hydroxide, ferric hydroxide, aluminium hydroxide, or barium sulfate. Some precipitates he has taken, and he was studying the diffusion property through the membrane. You call it parchment membrane bag. And he they found that the particles are not coming out through the parchment membrane. So then what he did, he estimated the particle size of those the particles of the suspension. So the particle size was found to be greater than 10 power minus 6 meter. He estimated the particles. Roughly I showed the diagram here. Suspension, freshly prepared precipitates. So these particles are not found to be passing through the membrane. He estimated particle size was found to be greater than or more than 10 power minus 6 meter. So I call this as the suspension, means the freshly prepared precipitate dispersed in a medium, we call it the suspension. So these suspension particles are also relatively bigger in particle. They are not found to be passing through the parchment membrane bag, and the particle size was found to be greater than 10 power minus 6 meter. Then Thomas Graham has taken the true solution or crystalloids. So crystalloids means the substances which possess a definite crystalline structure like sodium chloride, potassium chloride, cesium chloride. Already we have studied the solid state chemistry. So the structure is simple cubic lattice, BCC, FCC. We call it crystalloids. Substances which possess a definite crystalline structure, they are called the crystalloids. When these crystalloids are dissolved in a dispersion medium or in a water, we call it true solution. So this solution is placed in the membrane, parchment membrane bed, and he was found observing the diffusion property. He found that the particles of the two solutions are coming out quickly through the membrane. Very fast, they are coming out through the passing through the membrane very quickly. And then he estimated the particle size. The particle size of these the crystalloids at true solution was found to be less than 10 power minus 9 meter. Look at here the suspension particles. So the particle size was found to be more than 10 power minus 6 meter, and they are not found to be passing through the membrane, parchment membrane bag. And he has taken the true solution of the crystalloids he has taken. So these particles they are found to be passing through rapidly through the membrane, and the particle, they are very small particle, and the particle size was found to be less than 10 power minus 9 meter, and he called the crystalloids. Then what he did, he taken glue-like compounds. Glue-like compounds, for example, glue, gum, starch, gelatin, arabic, agar-agar. So they are all the glue-like compounds. He has taken all the glue-like compounds and studied one by one. He found that the particles are found to be diffusing very slowly through the membrane. So the glue-like compounds is placed in the parchment membrane bag, and he observed that the particles are coming out slowly, very slowly through the membrane. And he estimated the particles. It's very interesting. See these particles. If you look at the approximate, the size are given. So the particles, this is the glue-like compounds. You call it colloids. These particles are smaller than the particles of the suspension, but greater than the particles of the crystalloids. Look at the approximate the emission of this particle. So I represent the suspension particle, the crystalloid particle. So these are the particles, glue-like compounds called the colloids. So these particles was found to be, the size of the particles was found to be smaller than the particles of the suspension. Observe here. And then bigger than the particles of the true solution. And he estimated the particle size. The particle size was found to be in between 10 power minus 6 to minus 9 meter. And he called as these the substance he called as the colloids. That is so the suspension particle size was found to be so more greater than 10 power minus 6. And here the particle size of the crystallites was found to be less than 10 power minus 9. Not in between. The particle size varies between 10 power minus 6 to minus 9. They are called the colloids. So these colloids has been classified all the glue-like compounds. So their particle size was found to be in varies between 10 power minus 6 to minus 9 meter. And these substances they are called the colloids. So only the particle size is the criteria to classify the substance into the colloids. All the glue-like compounds, like again example, glue, gum, starch, gelatin, arabic, agar-agar, all these the particles were found to be, the size was found to be smaller than the particles of the suspension, bigger than the particles of the crystallites. They are found to be diffused very slowly through the particle membrane, and the particle size was found to be between 10 power minus 6 to 10 power minus 9 meter, or say in terms of nanometer 1 to 1000 nanometer, or they are called the colloids. So the particle size is the criteria to classify the substance into colloids. Based on the particle size, Thomas Graham, so they classified the substance into the colloids. That's why, so we can define the colloid means the colloid is any substance. It may be solid or liquid or gas whose particle size varies between 10 power minus 6 to 10 power minus 9 meter or 1 to 1000 nanometer. They are called the colloids. So basically I given the three differences: suspension and true solution and colloids. In comparison with the particle size, all the glue-like compounds, he called it the colloids. The particle size was found to be varies between 10 power minus 6 to 10 power minus 9 meter or 1 to 1000 nanometer. They are called the colloids. So colloids may be in any physical state. It may be in solid state, liquid state or gaseous phase. Only if the particle size was found to be varies between 10 power minus 6 to minus 9 meter, they are called the colloids. The term colloid was introduced by the Thomas Graham into the chemical literature. All the glue-like compounds he studied. So the diffusion property, they are diffusing very slowly through the parchment membrane. And the particle size was found to be in between 10 power minus 6 to 10 power minus 9 meter. Or the particle size of these colloids are smaller than the particles of the suspension, but bigger than the particles of the the crystallites. So based on the particle size here, it may be solid, liquid or gas whose particle size varies between 10 power minus 6 to minus 9 meter. They are called the colloids. So this is basic definition for the term colloids. I will continue further. So this the colloid, imagine you follow. So this colloid is not homogeneous. It is heterogeneous system. Colloids is a heterogeneous system consisting of two different phases. One is called the dispersed phase and dispersion medium. But a colloid is a heterogeneous system consisting of two different phases: dispersed phase and dispersion medium. What is the dispersed means the any substance which is distributed in the form of colloids. It will be solid or liquid or gas whose particle size varies between 10 power minus 6 to minus 9 meter or 1 to 1000 nanometer. So those particles is called the dispersed phase. So these particles are distributed in medium. Which medium? These particles are distributed in solid medium or liquid medium or gaseous medium. The medium in which these particles are distributed is called the dispersion medium. Therefore, you remember colloids is a heterogeneous system consisting of two different phases. So dispersed phase and dispersion medium. So dispersed means any substance which is distributed in the form of colloids, means based on the particle size. So we call the dispersed phase. So where these particles are distributed, what is the medium in which these particles are distributed is called the dispersion medium. Okay, I will give a small work for you because I am teaching over the video. I could not get your feedback, and I will try to answer on your own in sitting in the house. Now, so based on the physical state of the dispersed phase and dispersion medium, I will give a number of examples for the colloids. I will give the example. Try to you have to say when an example has been given to you. You have to say what is the dispersed phase and what is the dispersion medium, and that system has got a particular name. That name I will give you. But what you have to do is, when example has been given to you, you have to say what is the dispersed phase and what is the dispersion medium. I repeat, dispersed phase means any substance, it will be solid or liquid or gas, whose particle size is between that colloidal form 10 power minus 6 to minus 9 meter. They are called the colloids. But what is the medium in which these particles are distributed is called the dispersion medium. I will go back to the, look at this. First I will give the examples. You have to mention what the dispersed phase, then dispersion medium, then name of the salt. I will help you. Huh? I will take first I will give this example. Look at the example. I give the example alloys, what is colored glass, ruby glass, what is colored gems, pigmented plastics. Look at take the alloys as an example. In this alloys, you have to say what is the dispersion phase and what is the dispersion medium. Students, please can you say in the case of alloys, what is the dispersion phase and what is the dispersion medium? So the alloys, there is a mixture of two or more solid. Means it must be solid is a dispersion phase and solid is a dispersion medium. In the day, when solid is a dispersion phase, solid is a dispersion medium. It is called the solid salt. Name is called the solid salt. You can see the colored glass now. See the colored glass. Glass is nothing but the sodium silicate in which color pigments are so integrated. Well, both are solids, not solid in solid. Like the example of alloys, colored glass, ruby glass, or the colored gems, pigmented plastics, or even the marbles. Now, solid dispersed in solid is called the solid salt. Some example. I'll go to I'll give the example of muddy water, ink I have taken, paint I have taken. Some of the metal salts like gold salt, silver salt, starch dispersed in water, gelatin in water, agar. But so many examples I give. I will take first example, muddy water. I was saying muddy water when the rain is coming, water is flowing, muddy water. Can you say what is the dispersed phase in muddy water and what is the dispersion medium? So the muddy water contains solid mud particles. Dispersed, which is colloidal form. Solid is a dispersed phase. Where they are distributed, they are dispersed in the water, liquid. So in this, the solid is the dispersed phase. What is the liquid is the dispersion medium. It is called by the name of sol. Sol is a general name. What is solid? Dispersed in muddy water. Or you take ink. Ink consisting of the solid carbon particles dispersed in the liquid. Like this, so metals are gold dispersed in water, silver dispersed in water, or solid dispersed in liquid is a salt. Very simple example will appear even your board examination and also entrance examination. When example has been given to you, you have to apply your mind. Tell me what is the dispersion phase and what is the dispersion medium. See, simple example, muddy water you can take. You can see practically muddy water. It contains a lot of the mud, small mud particle which are in colloidal state, whose size is 10 power minus 6 to minus 9 meter. So this is a solid. But solid dispersed in liquid, it is called as the non-salt. Don't they call this a solution? It is a salt. Salt means solid dispersed in liquid is a general name given as the salt. Look at another example. For smoke, I have given smoke, dust, fumes. For smoke, what is the smoke consisting of? You have seen every day lot of the smoke from industries discharging in the atmosphere. Smoke consisting of carbon, solid carbon particles dispersed in the air. Smoke consisting of the dispersed phase is carbon particle solid. They are dispersed in the air. Smoke, dust, fumes. But solid is a dispersed phase. Means carbon, so the particles of the smoke they are dispersed in gas. So this is the part by the name they are called the aerosols. System has been given as the aerosols. What is the look at the example? I have taken a solid. So these are I have taken all dispersed. They are in colloidal form. But solid will dispersed in solid will dispersed in liquid, solid dispersed in gas. All the three cases are possible. So this is called the solid salt. You must show salt, solid dispersed in liquid, solid dispersed in gas is called the aerosol. So based on this physical state of the dispersed phase and dispersion medium, we give a large number of examples. Very common questions in most of the national level competitive examinations. Next, I will take the other example. I take ice cream getting. Ice cream. Imagine you are very crazy for ice cream. Ice cream, we have to say what is the dispersed phase and what dispersion medium. Similarly, butter, I have taken boot polish, cheese, medicines, jellies, jam, curd. So a simple example, take the ice. You can apply to other example. Ice. In the ice, what is the dispersed phase? What is the dispersion medium? How ice is made? They will take liquid in water. Water will be freezes into solid. Means liquid droplets of water. The dispersion solid. Liquid in the ice. Liquid dispersed in solid. That is dispersed phase is liquid, and that is the dispersed medium is solid. But liquid. So the ice cream is made from water only. Water is liquid. That becomes solid on cooling. So the solid. Liquid dispersed in solid. It is called as the gel is the name given. So they say liquid dispersed in solid. Even you can say butter, wood polish, toothpaste, all the example for the gel or liquid dispersed in solid. They all contains the liquid particles. They dispersed in solid. It is called a gel. But it's all solid in liquid, aerosol, solid in gas. So this is the liquid in solid is called the gel. This is also important. See, they ask the name of the system. You have to choose what is the dispersed phase and dispersion medium. Or they give the example. You have to choose what is the dispersed phase and what is the dispersion medium. So milk, I give example. Milk, blood, shampoos, cream, oil, put into water, or water put into oil. I take milk as an example. So milk, what is milk consisting of? Milk consisting of liquid fat particles, dispersed in liquid. Liquid in liquid. The milk consisting of the liquid fat particles dispersed in liquid. Liquid dispersed in liquid. It is called the emulsion. Emulsion is the, so the name of the system given. So for the liquid in liquid, like milk, blood, even the blood is an emulsion. Put shampoo, so the cream, so you can put oil into water or water into oil. Liquid in liquid is called the emulsion. So take one simple example. Analyze. Similarly, you apply what is the dispersive phase and what is the dispersion medium. Just I told you, colloids is a heterogeneous system. Is not a homogeneous system. Heterogeneous system consisting of dispersive phase and the dispersion medium. Two phases are there in the colloids. Look at this example. Again, the mist I will give. Very morning you can see the mist or fog. We call it the or rain. You can see clouds. Clouds. Insecticide spray. Or take the mist in the early morning. You can see what the dispersive phase in the mist. So small droplets of liquid, liquid dispersed in gas, in the dispersed in atmosphere. See, so the mist or fog or rain, this is the liquid dispersed in gas. So liquid dispersed in gas is called the, so liquid aerosols. They are called liquid aerosols. So called aerosol is the solid dispersed in gas. Liquid is liquid dispersed in gas. Liquid aerosols. But here you can observe here. So liquid, liquid, liquid. All, so the state is possible of colloids, dispersed phase. They may be dispersed in medium is solid in solid, solid in liquid, liquid in gas. All the state is possible here also for the example for the colloidal system. Next example we take the foam rubber, pumice stone, some gas inclusion. You can see beautiful natural occurring stone, some stone gas inclusions are there. So the rubber. Pillows, mattress. So what is the dispersal phase here? Gas is the dispersal phase. That is dispersal. You take a foam rubber, it compresses. So that is the gas is dispersed in the solid. The gas. So gas is dispersed in solid. It is called the foam. Solid. The name is called the solid foam. So this is the foam rubber, pumice stone. In pumice stone, so in the solid gaseous inclusions you can find gas dispersed in the solid. So the mattress you can see gas dispersed in solid is there for the solid foam. Another example is froth I have taken. Froth or say so refer the soda water. You say everybody using the soda water. So lather you can see or shaving cream or air bubbles, froth, lemonade froth. I will take examples of soda water. What is the dispersion phase and what is the dispersion medium? Soda water. You open the bottle. What happens? Here, gas bubbles will come in. Means the gas is dispersed in liquid. So this is liquid gas. So this is the gas is a dispersed phase. Liquid is dispersion medium. So this is called as the, or this is called the liquid. The name is called the liquid foam. Here the gas can disperse in solid foam. Gas can be dispersed in liquid. So liquid foam. In all the cases, I give an example. Solid can disperse in liquid, solid in solid in liquid, solid in gas. There are also liquid in solid, liquid in liquid, liquid in gas. So gas in solid, gas in liquid. Can you give one example for a colloidal system where gas is dispersed in gas? I will not give any example here. Can you give anybody can give an example in which gas is dispersed in gas? I want gas as a dispersion medium. Gas as a dispersal phase or dispersion medium. Can you give an example, my dear students? In all other cases I given. If you can take the solid dispersal phase, you can disperse in solid, disperse in liquid, disperse in gas. Liquid is a dispersal phase, you can disperse in solid, in liquid, in gas. Or here if you take the gas as a dispersal phase, gas in solid, gas in liquid. Then what is gas in gas? Can you give one or two example of the colloidal system where gas is dispersed in another gas? I hope no example. No, there is not. I will show the example. But a gas, the system does not exist. So gas in gas does not exist. So gas dispersal phase, dispersion medium. So no example is possible. Can you say why? Why gas in gas is not possible? Why no system dispersive phase and dispersion medium? Because I told you colloids is a heterogeneous system. So two different phases, but gas is homogeneous. It cannot form a colloidal system. So two different phases. One should be dispersive phase and dispersion medium. So gases are miscible in all proportion. So gas cannot have two different phases. Therefore, gas in gas, no system will exist. Based on the physical state of the dispersive phase and dispersion medium, some of the large number of example has been given under the colloids. I given the colloids. It may be the colloid may be solid, liquid, or gas, whose particle size varies between 1 to 1000 nanometer or 10 power minus 6 to minus 9 meter. So diffusing very slowly through the parchment membrane, we call it the colloids. But colloid is not a homogeneous, it is a heterogeneous system consisting of dispersive phase and the dispersion medium. Based on the physical state of the dispersive phase and dispersion medium, a number of examples are given for the colloids. So is there solid are given, but solid in solid, sol are given, but solid in liquid. So the aerosol, but solid in gas. So the very important. If you can apply your the concept, you can do well in your entrance examination also. Very common. You can see any national level competitive examination. One example will be there. You have to say what is the dispersive phase, what is the dispersion medium. Or we give the name of the system. In the system, what is the dispersive phase and dispersion medium. Like I said, mainly sol. Sol is solid dispersed in liquid. Or gel I will take. Gel is liquid, so dispersed in solid. Liquid dispersed in gel. You can imagine ice cream or toothpaste, but liquid in solid. So therefore, the emulsion, liquid dispersed and another liquid is part of the emulsion. Based on the physical state of the reactant, the physical state of the dispersive phase and dispersion medium, the number of examples are given for the colloidal system. Students, you please follow this table. Try to apply your mind. You take any more number of examples. So number of other examples are available in your NCRT. Please open and apply your mind. Say what is the dispersive phase and what is the dispersion medium in each colloidal system, and what is the name of the system. What is the sol? What is the emulsion? What is the gel? What is the aerosol? But all these names you should become familiar as early as possible in this chapter. Now, so welcome back, my dear students. I told you, colloids means it may be in physical state, it is solid, liquid, or gas, whose particle size varies between 10 power minus 6 to minus 9 meter, or you can say 1 to 1000 nanometer. They are called as the colloids. And the colloids come with diffusion property. They diffuse very slowly through the parchment membrane. And these colloids, it's a heterogeneous system consisting of two different phases, dispersive phase and dispersion medium. But a number of examples I have given for the dispersive phase and dispersion medium. So important system will be, I would say, what is sol? What is a sol? What is solid, dispersed liquid is called a sol. I give the example, best example, muddy water I given by using resin, ink, paint, metal salts. Or solid dispersed liquid is called the sol. What is aerosol? Smoke is an aerosol. Solid carbon particles are dispersed in air. What is solid in gas? Aerosol. Another important system is gel, in which liquid is dispersed in solid. Give example, ice cream, butter, food polish, toothpaste. They are all gel, liquid dispersed in solid. Then another example, milk and blood. Some of the example, like liquid dispersed in liquid is called the emulsion. What is solid dispersed in liquid is solid. Solid dispersed in gas is aerosol. So the liquid dispersed in solid is called a gel. Liquid dispersed in liquid is called the emulsion. Some of the important systems you have to remember. So here coming to the sols. I told you sol means the solid dispersed in liquid is called the sol. Some for practical application we can use the dispersion medium, different dispersion medium. Suppose solid dispersed in water, we are going to use the word like hydrosol. Sol is a name. If water is used, it's called the hydrosol. Very commonly, for practical application, we use water as a solvent. We generally say again the sol. If water is a solvent, we call it hydrosol. Suppose if alcohol is used as a solvent, we alcohol. So benzene is a solvent, we benzosol. Some the subname can be given. Sol is a general name. Solid, dispersed, and liquid. Suppose liquid used is water, we call it hydrosol. Alcohol, so the dispersion medium, alcohol. Dispersion medium is benzene, the benzosol. So different names can be given under this. Solid, dispersed, and liquid is called the sol. And different names based on the dispersion medium. Then we take up another important the point. So it's called the classification of the colloids. So the colloids, they are classified into two types: lyophilic colloids, lyophobic colloids. Leo means solvent liking colloids, solvent hating colloids. Lyophilic, lyophobic. Suppose solvent used is water, say, is called by hydrophilic colloids. So hydrophobic colloids, solvent liking, solvent hating. If solvent is used water, hydrophilic and hydrophobic. Have you important properties of these lyophilic colloids and lyophobic colloids. So if the solid is water, you can take hydrophilic colloids and the hydrophobic colloids. I'll give you the important differences between the lyophilic colloids and lyophobic colloids. So look at these lyophilic colloids. Look at the first example I give. All glue-like compounds. All the glue-like compounds are glue, egg albumin, gum, starch, gelatin, agar-agar. All the glue-like compounds are given under the lyophilic colloids. Look at the lyophobic colloids example. All the metal salts, means they are inorganic in nature: gold salt, platinum salt, silver salt, arsenious sulfate salt, ferric hydroxide salt, sulfur salt. That means they are made of inorganic origin. They are made of organic origin. Just look at the example before going the differences. Solvent liking colloids. All the glue-like compounds, they fall under the lyophilic colloids. All the inorganic, of origin, they are part of the lyophilic colloids. What is meant by lyophilic colloids? So lyophilic colloids are the substances which can be easily converted into dispersion medium. The substances which can be easily converted into the colloids. So the simple method of by mixing or by shaking or warming, you take a starch, put water, you shake, simple method of shaking. So it forms the colloidal dispersion. That means some substances have got more affinity for the dispersion medium. They can be easily converted into colloidal dispersion. They are called the solvent liking colloids. They are called the lyophilic colloids. Lyophilic colloids have more affinity for the dispersion medium. They can be easily converted into the colloidal dispersion. They are called the lyophilic colloids. Lyophobic colloids are substances which do not have affinity for the dispersion medium and cannot be easily converted into dispersion medium. Unlike simple method of mixing, shaking, warming, we cannot prepare the colloidal dispersion of the lyophobic colloids. We require some chemical reaction like oxidation, reduction, hydrolysis, double decomposition, or some electrical method. Some difficult method has to be employed to convert this, the lyophobic colloids. They have no affinity for the dispersion medium, which cannot be easily converted to colloidal dispersion. They are called the lyophobic colloids. Lyophilic colloids, I told you, of organic origin. They got more affinity for the dispersion medium. They can be very easily converted into the colloidal dispersion. So lyophobic colloids, made of inorganic origin, are given, which cannot be easily converted into colloidal dispersion. They have no affinity for the dispersion medium. Some chemical methods or physical method has to be employed to prepare the colloids. They are solvent hating colloids. They are called the lyophobic colloids. So these lyophilic colloids, they are reversible. What is reversible means? Suppose I will take I'll take the starch. I'll put a water and shake it. You'll get a starch solid form. Suppose I will evaporate, heat it. So we'll get a residue back starch. Again I put it in the water. Again shake. Again we'll get the colloidal dispersion. That means solvent can be removed by evaporation and again reconverted into the colloids by adding the dispersion medium. They are reversible. So these lyophilic colloids are reversible. Means they can be precipitated, or by evaporation, or by any other means. They can be precipitated and again they can be converted back into the colloidal dispersion. They are called the reversible. But lyophobic colloids are irreversible. And once precipitated, they cannot bring back to the colloidal dispersion. They are called irreversible. So once these particles are precipitated, again into whatever the way, so it cannot get back to the colloidal dispersion. So they are called irreversible. And also the most important is stability. So these lyophilic colloids, they are more stable. Lyophobic, they are less stable. Why the stability is due to? Because these lyophilic colloids, they got a solvent liking. Every colloidal particle has got a layer around the colloid. Say suppose if we take a particle, so this is a colloidal particle. So this is having a solvent layer around because it is solvent liking. So this is the more stable. And then lyophobic is a particle. It has no affinity for the dispersion medium. It has no solvent layer. So this is the more stable. This is the less stable. And this so both can be precipitated by adding electrolyte. So suppose if you want to precipitate, we require more amount of electrolyte because you have to break the solvent barrier. More amount of electrolyte is equal to cause coagulation. While a small number of electrolytes they can be coagulated. That shows lyophilic colloids are more stable and lyophobic are less stable. Lyophilic are more stable because they got the protective solvent here. They are less stable due to the absence of the solvent here. So stability indicates they cannot be easily coagulated. These particles are stable. They cannot be easily coagulated. Even if you want to coagulate, we require large amount of electrolyte for the coagulation. But they can be easily coagulated by adding a very small amount of the electrolyte. So this is they are of organic origin, but all the blue-like compounds they are inorganic origin. All they are prepared of inorganic origin. So why I am telling this point is because in the examination they give an example. You have to say whether it is a lyophilic or lyophobic colloid. You have a general idea. Lyophilic means they are of organic origin. So in any organic origin, organic molecule in it, see there we can say is a lyophilic colloid. Any inorganic origin it comes under the lyophobic colloid. And if you come to one more property, so these lyophilic colloids, I'll take hydrophilic colloids, they have lower surface tension and higher viscosity than water. If you compare the property of surface tension viscosity, it has a lower surface tension and higher viscosity when compared to the water. But this lyophobic, so there the surface tension and viscosity are almost similar to the water. Now if you take the water as a solvent, so we call it hydrophilic and hydrophobic. So these hydrophilic salts have lower surface tension. This is also a multiple choice question. They have lower surface tension and higher viscosity than water as a dispersion medium. Here both the properties are similar to that of the water. Important differences between the lyophilic colloids and lyophobic colloids. So you are going to classify the number of types of colloids. I defined colloid. I told you it's a heterogeneous system, dispersive phase and dispersion medium. Depending upon the physical state of the dispersive phase and dispersion medium, we can give the number of examples like salt, gel, emulsion, aerosol. So number of examples has been given. Depending upon the affinity for the dispersion medium, we are classified into lyophilic colloids and lyophobic colloids. Solvent liking colloids, solvent hating colloids, they can be easily converted to colloidal dispersion. They cannot be easily converted to colloidal dispersion. So they are reversible, they are irreversible. They can be evaporated and again get back by adding the solvent. They are reversible. Once precipitated, we cannot revert it to the colloidal system. Irreversible. They are stable on account of the protective solvent layer. They are less stable due to the absence of solvent layer. So both can be coagulated by adding an electrolyte. But because more amount of electrolyte, because of more stability, more amount of electrolyte is required to cause the coagulation. By adding a small amount of the electrolyte, we can think about the coagulation. So lyophilic colloids, example of organic origin are given, they are mainly of the inorganic origin. But they depending upon the affinity towards the dispersion medium, you are classified into lyophilic colloids and the lyophobic colloids. One more classification, take the classification based on the type of dispersive phase particles. So based on the dispersive phase particle, further colloids are classified to multi-molecular colloids, macromolecular colloids, and associated colloids. You follow me carefully. They all know the new technology, but not difficult. We can understand easily. But in multi-molecular colloids, in the adsorption I told you. So van der Waals force of attraction, multi-layers are formed. Simply this is not specific in reaction. Any molecules can accumulate by another molecule. Physical adsorption takes place by the multi-layer. The same concept. So multi-molecular colloid means initially when the particle has been disposed in the solvent, they are in atomic form or molecular form. The atomic form, molecular form means size will be less than 1 nanometer. You have to bring to 1 to 1000 nanometer. Oh, what happens? There the van der Waals force of attraction. Atoms or molecules aggregate by van der Waals force of attraction, one layer over another layer. Thereby they form a colloidal system. They are called as multi-molecular colloids. So the multi-molecular colloids, example of sulfur salt. Sulfur is an atom, but gold is an atom, silver is an atom. How they form a salt? Aggregation by physical van der Waals force of attraction. One atom accumulates with another atom, so that they keep on increasing their size. Size become 1 to 1000 nanometer, like the sulfur. So this is called physical absorption takes place, and multi-molecular layers are formed. So these atoms are seen as sulfide is a molecule, but ferric hydroxide is a molecule. How it become a colloid? By the multi-layer physical absorption. One layer is absorbed another layer. Thereby they attain the size of the colloidal particle. They are called multi-molecular colloids. Before when these particles are dispersed in dispersion medium, they may be in atomic state or they may be in molecular state. Only by simple van der Waals force of attraction. So they accumulate one over the another by multi layers are formed by physical absorption. They will gain the size of the colloidal particle between 10 power minus 6 to minus 9 meter. They are called multi-molecular colors. Example I given: sulfur salt, gold salt, silver salt, arsenic sulfate salt, ferric hydroxide salt. They are called atom, gold atom, silver atom. How they become colloidal particle? Gold atoms accumulates one atom or another atom. So keep on by van der Waals force of attraction, multi-layer adsorption is formed. Finally, they attain the size of 1 to 1000 nanometer. The gold salt or silver salt, they are the multi-molecular colloids. Okay, my students. Then I will take the macromolecular colloids. So macromolecular, I take the example of starch, cellulose, protein, even the polymers. You know, they are the big molecules. You know. They are the big molecules. They are high polymers. Then how they become the colloidal particles? So when they are dispersed in water, the breakdown of the bigger molecules will take place and thereby attain the size of the colloidal particles. They are the macromolecular colloids. For starch, cellulose, protein, they are big molecules. So they got a bigger size. When they are dispersed in water, the chain will be broken to form the particles of the colloidal dimension, and such, you know, the colloids are called the macromolecular colloids. Look at the example: starch is a macromolecule, cellulose is a macromolecule, protein is a macromolecule. So even the polymers are the macromolecules. They are big molecules. So a longer the polymer chain. When they dispersed in the dispersion medium, so the chain will be broken to attain the size to 1 to 1000 nanometer or 10 power minus 6 to minus 9 meter. So they are called the macromolecular colloids. Very simple questions will appear. I will tell you one more board examination, even the all national level examination. The concept is simple. Only you have to understand properly. Then I will take the associated colloids. What are the to explain the associated colloids? I have taken the soaps and detergents. Soaps and detergents are the example for associated colloid. You know what is a soap? Soap or detergents, you know, at the low concentration of soap, it acts as an ion. So when the concentration of the soap has been increased, you know, so these you know, the ions, they associate themselves to form a spherical molecule called mesyl, of, you know, the color dimension is formed. Well, explain how, you know, the associated colloid, how mesyl is formed. What is the example of soaps? And the soaps, they are synthetic soaps. Synthetic soaps are detergents. So both are the example for associated colloids. You know what is a soap? I hope you know what is a soap. Soap is a sodium or potassium salts of fatty acids. What is a fatty acid? Long chain monocarboxylic, long chain monocarboxylic acid like lactic acid, myristic acid, palmitic acid, stearic acid, oleic acid, linoleic acid, linolenic acid. They are all fatty acids, you know, found in animal fatty acids. So long chain monocarboxylic acids. So these fatty acids, when boiled with soap, sodium salts of fatty acids are formed, or potassium salts of fatty acids are there called the soap. Sodium salts of fatty acids are washing soaps. Potassium salts of fatty acids used for bathing purpose. Soaps are generally sodium or potassium salts of fatty acids. I'll give you examples. I'll give you an example. So I'll take the example of, say this is the, so I'll take a stearic acid. This is C17H35 long chain carbon atom. So the COOH monocarboxylic acid. So it's stearic acid. When reacts with sodium hydroxide, so hydrogen atom is replaced with sodium. So sodium stearate is a soap, or sodium stearate is a soap used for the washing purposes. The sodium stearate undergoes ionization to form C17H35 long chain. So the carbon atom COO minus. Put Na plus. This can be all washed away. So this is the soap is nothing but the negative charge is there. So if you represent this is the soap in the form of structure. So this C17H35 is nothing but the CH3, CH2, 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 CH long chain. Or COO minus. That is soap is nothing but I'll put in the formula diagram. What is that? Long chain. Long chain. So this is the negative charge. Negative it will be the COO minus. So this is the the soap. Soap has got a COO minus is a negative charge. This is a long chain. This is CH2 long chain hydrocarbon chain with a polar head. This is simple. Yes, in electrolyte is a soap ion like a negative charge. And this ion, this is called the hydrophilic end. This is like a solvent, water. So this is hydrocarbon. It's a solvent. As you know, the organic compounds are insoluble in water. That's a general property. So this is solvent hating end. So this is solvent liking end. If you take the soap, Normally, soap is an ion, long hydrocarbon chain with a polar head. So this polar head has got a negative charge, CO minus. So this is solvent liking. So this is solvent heating. At low concentration, put it reaction in ion. So this is the negative reaction in ion. You go on increasing the concentration. Up to a particular concentration called the critical visual concentration. What happens, all the solvent liking will come to one side. All the solvent heating will come to one side. Here a spherical molecule is formed. That is called the missile. Look at this missile actually. And how this is the missile is formed. This one soap ion, this is the combination of say 100 number of the soap ions. 100 or 200 number of soap ions combined to form a spherical molecule called the missile. All the solvent liking will come towards one end. All the solvent heating will point toward the center. A spherical molecule is formed. This is called the missile is formed. This is an example for the associated colloids. Soaps and detergents are the example for associated colloids. At low concentration is an ion. It acts as an ion. Go on increasing the concentration at a particular concentration and a particular temperature called Kraft temperature. So these, more numbers, say 100 number or 200 number of these ions associate to form a spherical molecule of colloidal dimension. They are called the missile. How they associate? All solvent liking will come towards one end, pointing outwards, and all the solvent heating. So this is the they are friendly. All solvent heating will join together. Solvent liking will come at one place. So they are pointing outwards. Solvent liking. So pointing at the centers. All solvent heating. A spherical molecule is formed. So the what is the particle size is 1 to 1000 nanometer, 10 power minus 6 to minus 9 meter, and this is the example for the associated colloids. Soaps and detergents are the example for the associated colloids. So these are the what I told you. This is the based on the type of dispersed phase. You have taken the multi-molecular colloids, macromolecular colloids, and associated colloids. Multi-molecular term is atoms. In the beginning, they may be atoms or molecules. Simply van der Waals force of attraction, the aggregates, multi-layers are formed to attain the size of the colloidal particles. Again, example of these are sulfur salt, gold salt, silver salt, arsenic sulfate salt, ferric hydroxide salt. They are all multi-molecular colloids. Macromolecular means the starch, proteins, polymers or nucleic acids. So these polymers are big molecules. When they put into the dispersion medium, they break, undergoes cleavage to form so the particle dimension of 10 power minus 6 to minus 9 meter, they are called macromolecular colloids. Associated colloids are the soaps and detergents are the associated colloids. Soap is a sodium or potassium salts of fatty acid. At low concentration, simply reacts as an ion with a polar and negative charge. When the concentration is increased at a particular concentration, we call it critical missile concentration, CMC, critical missile concentration, at a particular temperature called Kraft temperature. So these large number of these ions, so they associated colloids, associated to form a spherical molecule. How they associate? When associating, all the solvent liking will come towards the end. Solvent heating will come to the center. A spherical molecule is formed. What the particle size was going to be 1 to 1000 nanometer or 10 power minus 6 to minus 9 meter. So they are part of the associated colloids. So this diagram I show here. So this is at low concentration soap is an ion. It's a hydrocarbon chain. Is a tail. Hydrocarbon tail is a hydrocarbon tail. As a hydrocarbon solvent heating disease. So the CO minus is a polar head is a solvent tail. When the concentration is increased, they associate. More number of these soap ions associate to form a spherical molecule. So this is called the associated colloids. Okay, friends, you can understand there are three types of the macromolecular, so the multimolecular colloids, macromolecular colloids, and associated colloids. Okay. So this missile formation. So this the missiles are formed the associated colloids. How this concept can be used for cleaning. The cleaning action of soaps. You have to explain the cleaning action of soaps. I will explain how the cloth will be cleaned. Look at this diagram. Cleaning action. Suppose you imagine it is a cloth. Say imagine it is an oil stain. Some oil is put on the cloth. You put the soap. It become clean. How it will become clean? Science will not accept it without any proof. You need explanation. So the cloth is there. A drop of oil has been dropped on the cloth. You while washing, you put a soap. It will be washed away. How will it be washed away? So imagine it is a cloth and this is a eye drop. Now wash with a soap. What is a soap? Is a long hydrocarbon chain with a polar end. So this the oil stain is also hydrophobic, is a solvent 80. So this will be outside the water solvent will be there. So these soap the ions. So this hydrocarbon chain helped into the oil because this solvent 80 is solvent 80. Or hydrophilic solvent taking is pointing towards the solvent. Then what happens? Over applying the soap as a critical concentration, soap increases. So these the hydrocarbon chain pull away the oil drop. It will keep on pulling away because the solvent taking water is there. They are attracted towards the water. They pull away the soap ion. Then this leaves the surface. How it leaves the surface? While living, it forms a spherical molecule. It forms a spherical molecule. This oil drop on the cloth will become a spherical design is formed. This can be washed away by the water and cloth can be cleaned. Any oil or dirt can be cleaned by washing. So the cleaning action is soaps and detergent can be extended by the micelle formation. At low concentration is an ion. So that ion is pegged into this the oil cloth. This is a hydrocarbon chain CH2, 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 CO minus. So this is also oil is a hydrophobic. This is also hydrophobic. Solvent taking. If the hydrocarbon chain is pegged into the oil drop. So the binding outwards and towards the water is there for washing. They are attracted towards the water. They drag the oil drop. By dragging water gradually the oil leaves the surface of the cloth. How it leaves? It will become a spherical molecule. This can be easily washed away by the running water. For cleaning action, soap can be explained by the micelle formation or associated colloid. But soaps and detergents are the associated colloids. How the soap will become a colloidal particle, a micelle. How this micelle function can be used for cleaning the cloth. Okay, right, students? Fine. Okay, this is all some of the fundamentals I given about the colloids. Now we have to go for the preparation, properties and application of colloids. For the preparation of colloids, because these colloids has got a wide applications in the field of medicine. You have to prepare the colloids. They use in the skin treatment, eye treatment, so over a injection, intramuscular injection. They are all used in the form of medical. You have to prepare these colloids, and you have to purify it because it will be injected in the human body. Is used for eye treatment and skin treatment. It is purified. How colloids are prepared? How they are purified? That is the next point for discussion. Now take now the preparation of the colloids. So they take the lyophilic colloids and lyophobic colloids. So preparation of lyophilic colloids is very easy. As I told you, they are solvent taking. Simply you take the substance, you put some solvent or dispersion medium, you shake it or warming it, it will become a color dispersion. So the salts of starch or glue or gum or gelatin is easy to be simple method of mixing or by warming. We can prepare the color because they are solvent taking. But only the problem we are facing with the lyophobic color, which have got more medical application. How to prepare this lyophobic, the salt. I will take mainly salt, means solid dispersed liquid. I will call the salts I will take for medical application. So preparation of these salts, so that lyophobic salts by chemical methods and dispersion methods. Chemical methods are used. Chemical methods like oxidation, reduction, hydrolysis, double decomposition. Number of chemical methods can be applied, and dispersion, the physical methods. Dispersion method, you can use the Bredig-Sorb method and vaporization method. I explain all this method, how the salt can be purified. First, I will take the chemical methods. But the chemical methods, I told you, some of the chemical reactions can be obtained, like hydrolysis. So I want to prepare ferric hydroxide salt. How ferric hydroxide is obtained? I will take ferric chloride. I put the hot water. You shake this. But the ferric will become ferric hydroxide. And this ferric hydroxide, I told you, it is a molecule. It what happens? It undergoes multi-molecular adsorption. Finally, ferric hydroxide salt and ferric hydroxide salt is formed. This comes under the multi-molecular colloids. This is a molecule ferric hydroxide. So this is by physical adsorption and aggregation takes place to form the colloidal dispersion of ferric hydroxide. Preparation of the sulfur salt. I will take sulfur dioxide and H2S. Sulfur dioxide pass H2S. Sulfur dioxide is an oxidizing agent. Oxidize hydrogen sulfide into sulfur. Sulfur salt is obtained. Again, multi-molecular colloids, sulfur aggregates to form the colloidal sulfur. And the gold, the gold chloride, stannous chloride is a reducing agent. This stannous chloride reduces the gold chloride into gold. Gold salt can be prepared by reduction process, oxidation, hydrolysis, double decomposition by mixing arsenious oxide or passing H2S. For double decomposition, break this. This is double decomposition takes place. Arsenious sulfide and H2. Arsenious sulfide salt can be prepared. So using some chemical methods. So these lyophobic salts can be prepared. Unlike lyophilic colloids, very easy, simple mixing and shaking we can prepare the lyophilic colloids. So lyophobic cannot be prepared. Some chemical methods, some chemical reactions like hydrolysis, oxidation, reduction, double decomposition. Some the chemical methods are employed to prepare the lyophobic or hydrophobic colloids. These are the chemical methods. Under the physical methods, under this person we are taking Bredick's arc method. But Bredick's arc method. So this method is mainly used to prepare the metal salts. Metal salts especially means the gold, silver, platinum. You can't use all metal. You can't use iron. You can't use copper. You can't use other. Only the noble metals. They are high stability. So metal salts like gold, silver, platinum, they can be prepared by the gold salt by Bredick's arc method. I will explain the Bredick's arc method preparation of gold salt. Your NCERT syllabus has given preparation for the gold salt. But you can prepare any metal salt, your platinum salt, silver salt, any metal salt. So the noble metal salts, they are used for medical applications. They can be prepared with the Bredick's arc method. In the Bredick's arc method, what we do? So this, suppose I want to prepare a gold salt. Our two gold wires are taken. These are the two gold wires dipped into the dispersion medium. Not simple. You can write the diagram. This is self-explanatory. You can label, we can MRs. So I have taken the two gold wires are taken. Say I want to prepare a gold salt. If you want to prepare silver salt, you take silver wire. Or take a platinum salt, you take platinum. So I take gold as an example. Two gold wires are taken deep into the dispersion medium. So this dispersion medium is kept immersed in the freezing mixture. Ice and salt, not freezing mixture. By you pass, high voltage of electricity is passed. Means electric arc is produced. Between the two copper and this you current like this, arc is produced. When the arc is produced, what happens? High temperature is produced. Imagine what happens high temperature. Some of the gold atoms vaporizes. But if you are producing the atoms, you are taking the gold wire, passing the current, high temperature gold atoms are produced. So these gold atoms are produced, they are suddenly cooling. What happens? The aggregation takes place. One atom aggregates to another atom. So simple one was force of attraction. So the atoms accumulate one over the another. Finally, the metal gold salt can be obtained. So this process of accumulation will keep on taking place. And they may cross the size of the colloidal dimension. They will not work as a colloids. Strictly, their particle size should be 1 to 1000 nanometer or 10 power minus 6 to 10 power minus 9 centimeter. For further aggregation, you are going to put a small amount of the potassium hydroxide added as a stabilizer. Because something is done for stabilization. At some stage, you have to break the aggregation. A small amount of alkali potassium hydroxide added that terminates the aggregation. And finally, the colloidal salt can be prepared. Gold salt can be prepared. Medically, it is called as the purple of Cassius. The name has been said, technical name purple of Cassius. Gold salt can be prepared by the Bredick's arc. Students, can you understand? It is a simple method of preparation. So you can write on your own words or write a diagram, label the parts. To perfect to the gold salt preparation, I have taken the two gold wires are taken deep into the dispersion medium. Say water as a dispersion medium. So this dispersion medium is kept immersed in the freezing mixture. In salt and water. Freezing mixture is salt and water. So high voltage of current is passed through the gold wires. You produce an electric arc. Just to touch it and keep it. Electric arc is produced. When the electric arc is produced, the gold atom dispersion called it. For dispersion method, gold dispersed into atoms. So these atoms, what happens? Because sudden cooling, aggregation takes place. One atom or another atom, they aggregates by multi-molecular absorption. Finally, the colloidal size will be formed of colloidal particle. So this aggregation may take place. They may cross over the colloidal particle. To prevent a small amount of alkali like potassium hydroxide is used as a stabilizer to keep the salt stable. So the gold salt can be prepared by the Bredick's arc method. Okay? I'll go to the peptization. Another method is called the peptization method. In this peptization method, what we do now? So the freshly prepared precipitate can be converted to colloids by adding an electrolyte but having common ion. If all ma'am, using a very simple sentences I am using. I will take a freshly prepared precipitate. Freshly prepared precipitates can be converted into colloids by adding an electrolyte having common ion. I'll give the example. Say, I take the ferric hydroxide precipitate I have taken. I will put it to the ferric ions. Ferric ions is a dispersion medium. So this is the I will take ferric chloride as a peptizing agent. So iron, common ion. This iron absorbs Fe3 plus ion. This is ferric hydroxide. This is a surface current absorbs Fe3 plus ion. But the colloidal ferric hydroxide solid is formed. It's called peptization. You are converting the freshly prepared precipitate into colloids by adding a suitable electrolyte. Not adding a common ion. Iron is common. Such electrolyte you have to choose. This is a peptizing agent. So these the precipitate absorb the charges from the dispersion medium, not get converted to colloidal particle. Ferric hydroxide solid is formed. Suppose I take down AgI precipitate. I put in the dispersion medium Ag plus. I put a silver chloride. Put Ag plus Ag. It forms AgI, absorbs Ag plus. Colloidal silver hydride is formed. Or in the dispersion medium, I use I minus. You put potassium iodide I minus. Then I absorbs I minus ion, but here negative charge is formed. That is in this peptization method. We can convert the freshly prepared precipitates into colloids by adding a suitable peptizing agent or an electrolyte. We should have a common ion. So they absorb the common ions from the surface, and there will be the precipitates will be converted to colloidal dispersion. If that process is called the peptization. During peptization, the precipitate absorbs the charges from the dispersion medium, and thereby they will convert to colloidal dispersion. This process is called the peptization. What is the peptization process? One more question. The conversion of freshly prepared precipitates into colloids. How? By adding a suitable electrolyte having a common ion, or by adding a suitable peptizing agent having a common ion, is called the peptization. By peptizing agent methods, the number of the lyophobic colloids can be prepared. Okay? Well. Okay, this is about the preparation. Now we will go to the properties. Okay, again the preparation of colloids. Then what are the other you have to go for purification, because I told you salts are prepared. During these salts we are going to use number of electrolytes. So those the electrolytes, they will make the salt unstable. Immediately after preparation you have to purify. The salts are purified. The salts are purified by dialysis, electrodialysis, electroosmosis and ultrafiltration. Only dialysis, electrodialysis has been given in the NCERT syllabus. I put some more electroosmosis and ultrafiltration for your multiple choice point of view for national level. I will include. They are not much difficult. I will cover here only. On dialysis and the electrodialysis, electroosmosis, ultrafiltration. Some of the methods employed for the purification of the salts. But salts are prepared by different methods. By physical methods or chemical methods. They contain the crystalloids or ionic impurity. Those ionic impurity will make the salt unstable. To make this salt stable, you have to immediately go for the purification. One such method is called the dialysis. In the very first period I explained. So this is the diffusion property of the colloids and crystalloids. So you put the properties. The crystalloids, they diffuse rapidly through the membrane. Colloids diffuse slowly through the membrane. This is a fractional difference in the diffusion property. So crystalloids means ionic impurity. They diffuse rapidly. But colloidal particles diffuse slowly. But taking this advantage, salts can be purified by dialysis. That means you have taken this is a dialyzing membrane. We take a dialyzing membrane. So the salt to be purified is taken, suspended in the water, running water. What we are adding water here, water flows continuously, is a running water. Simple law experiment technique. So this is the parchment paper bag is taken. Salt to be purified is placed in the bag. Parchment membrane bag or the dialyzing membrane bag, and this bag is suspended in the running water. As per the diffusion property, all the ions, it contains ionic impurity, sodium, potassium, any ions, they diffuse rapidly through the membrane. They are carried away by the running water. So by the time few colloidal particles will also come, the loss will be there. But after some time, the two salt will be different. All the ionic impurity can be carried away by the running water. The salt can be purified. So simple, the experiment developed here for the purification of the salts. We are going to use the dialyzing membrane. The salt to be purified is taken. So this is kept suspended in the running water. The water should be running continuously. By fractional difference in the diffusion property, Now colloids means the crystalloids. Colloids diffuse slowly. See, if the 100 number of ions diffuse, one colloid may diffuse. They diffuse slowly, but crystalloids diffuse rapidly. When they suspend in running water, all the crystalloids or ionic impurity, they quickly passes through the membrane and they carried away by the running water. The pure salt left inside the parchment membrane bag is a dialysis. But as I said, it is not very fast process. It is a very slow process. I told you the colloids and crystalloids. Colloids diffuse slowly, crystalloids diffuse rapidly. We cannot. It is a very slow process. We have to wait for another 24 hours of the day to carry out the preparation for 100 ml of salt. But I want to increase the rate of this process. How we can increase the rate of the process? Can you think over? I want the separation of ions has to be separated by dialysis. I want to increase the process, the rate of process. That will be done by electrodialysis. What simple principle is? So I take this bag now. I'll put one electrode here. I'll put one electrode here. This positive plate, negative plate. You pass electric current. What happens? So the ions are charged particles now. They are attracted quickly towards the opposite charge plate. Positive has moved to negative plate, negative has moved to the positive plate. Quickly separated, and quickly the rate of process can be separated. They are carried away with the running water, and the rate of this process can be increased. That is called the electrodialysis. I'll show diagrammatically. So this is a simple process of dialysis. It is a slow process. See, apply the electric field here. Apply the electric field between this, the salt. So the ions will be easily moved because ions are easily attracted towards the opposite charged metal plates. Positive ions move towards the negative plate, negative ions move towards the positive plate. They are moving towards the opposite charged electrodes. Ions are quickly moved towards the opposite charged electrodes, and they are carried away in the running water, and the salt can be purified at higher rate. And this is called the electrodialysis. Electrodialysis is one such method for the purification of the salts. In industry, this electrodialysis is also used for the purification of water. Seawater, seawater contains a rich number of salts, sodium chloride, ionic impurity. This is what it can be. This is called electrode. So it is a chamber you can see in the industry they employ. So this is a dialyzing membrane, and you have taken the the soil has been taken here, or the seawater is taken here. Here the metal plates are adjusted here. Here the water is placed in the compartment. When seawater is placed in the middle compartment, you pass the electric current. So seawater contains mainly salt, Na plus Cl minus. Na plus ion move towards the negative plate, Cl minus move towards the positive plate, they move towards the electrode. Pure water left behind. This can be used for the the purification of seawater for the domestic applications. So this is the electrodialysis. This dialyzing membrane is used to carry out the separation. You can see. So this this dialysis nowadays is also used for the purification of blood for the patient suffering from kidney failure. They call the dialyzer. Diabetic patients periodically they go to the hospital because when the kidney has been failed, so mainly by biochemical reactions in our body, mainly urea and uric acid is produced. Kidney cannot filter. That urea uric acid enters the blood. They are all toxic compounds. When the kidney is filled, what happens? So this is a dialyzing membrane. So this is a patient. His entire blood is drawn. Sent to the dialyzing membrane. So this dialyzing membrane removes all the ionic impurity. The blood is purified, and again the pure blood will be sent back to the patient. Same dialysis that can be applied for the diabetic patients who have kidney failure. So all the toxic ionic impurity in blood can be removed because blood is a colloidal particle. So the colloidal particles diffuse slowly, but the crystals will move fastly. So by this, so dialysis can also be used for the patients suffering from the kidney failure. This is one diagram I given for the dialysis, application of dialysis. What is also, so the patient is undergoing a dialysis in the hospital. But what is called the electroosmosis? This is not there in our NCR, but you please, there is no much difference. Only in the electrode, you are going to use a semi-permeable membrane. So if you take the dialyzing membrane, colloidal particles will diffuse slowly. But you take the semi-permeable membrane, does not allow any colloidal particles. Only charged particles like ionic impurity can be passed away. This is the soil is placed in between the semi-permeable membrane, but the electric field is applied here. Ions are quickly separated more towards the upper charged plates, and the pure salt will be obtained. Why is called the osmosis? Again, because there increase the forces is called the electron osmosis also is employed for the purification of the sound. One is the ultrafiltration. It is not figured in our NCERT book. Ultrafiltration means you must know one basic idea. Colloidal particles has got this size from 10 power minus 6 to minus 9 meter. You cannot purify by common filtration. If you use a filter paper, colloidal particles will pass through. Then for that, what you got is ultrafiltration. Ultrafiltration means you are going to use a specially prepared filter paper. So you take ordinary filter paper. Ordinary filter paper is impregnated with colloidal, and this is hardened by formaldehyde. So this is the ultra filter which does not allow the colloidal particles to pass through. So this one is colloidal. Colloidal is prepared by adding the nitrocellulose. 4% solution of nitrocellulose in alcohol and ether. We take alcohol and ether, 4% solution of cellulose, nitrocellulose. So this is impregnated with the ordinary filter paper. That is further hardened by formaldehyde. This is called ultrafiltration. Through the ultrafilter paper, colloidal particles will not pass through. Again, colloidal filtration. You must know the multiple choice point of view. So these colloidal particles will pass through the ordinary filter paper. We cannot separate by filtration. Specially prepared filter paper has to be used. We call it the ultrafiltration. When the filter paper use this, so the filter paper is impregnated with colloidal. Colloidal is nothing but the nitrocellulose dissolved in alcohol and ether to get 4% solution. Further hardened by the formaldehyde. So through this filter paper, the colloidal particles will not pass through and it can be then purified. So these techniques are employed: dialysis, electrodialysis, electroosmosis, and we got the ultrafiltration. Some of the techniques employed for the purification of the colloids. Okay, friends. Now, the most important study in this chapter is the property of the colloids. Property of the colloids. So this the colloidal particles has got a particular dimension, 10 power minus 6 to minus 9 meter. Then what are the special properties shown by these colloidal particle? One is the kinetic property, optical property, and electrical property. The kinetic property, optical property, electrical property. Now take the kinetic property is called the Brownian movement. So Brownian movement, these colloidal particles, these colloidal particles will continuously move in a zigzag manner in the dispersion medium. This zigzag motion of the colloidal particle in a dispersion medium is observed by a scientist called Brownian. He is working on the pollen grains. He observed that these colloidal particles will move in a zigzag manner in the dispersion medium. So this zigzag, non-stop, continuous movement of the colloidal particles in the dispersion medium is called the Brownian movement. This is the kinetic property of the colloids. So these look at the property. This particle has got the zigzag, non-stop movement of the colloidal particles in the dispersion medium. So these colloidal particles, so it is very important, is they will not settle at the bottom. They will be suspended in the medium. They will they overcome the gravity. They will not affected by the gravity of acceleration due to gravity. Simply they are suspended in the medium. They are moving continuously in a zigzag manner. And this is observed by the Brownian is called the Brownian movement, the kinetic property of the colloids. Kinetic property, or you can say mechanical property. Then what is the cause for the particle? A short distance of the particle is moving in a zigzag, non-stop, continuous movement of the colloidal particles in the dispersion medium is called the Brownian movement. Then, what is the cause for this Brownian movement? Can you imagine what is the cause for the Brownian movement? Where do these colloidal particles gain energy? Because if they want to move, they should get the energy, kinetic energy. Where do they get? Look at the interesting point. These colloidal particles, so the zigzag or the continuous movement of the colloidal particle is due to the continuous impact of molecules of dispersion particles to the colloidal particles. Because the medium has got the particles. So the particles in the medium, dispersion medium, they constantly collide with the colloidal particles. Thereby colloidal particles gain energy, start moving in all the zigzag manner. This is called a Brownian movement. But zigzag, non-stop, and continuous movement of the colloidal particles in the dispersion medium is called the Brownian movement. This Brownian movement is the example of kinetic property. Where do these particles will get the kinetic energy? Because of the continuous collision of the molecules of the dispersion medium or the particles of the dispersion medium. They have a constant collision with the colloidal particles. Thereby colloidal particles gain kinetic energy and move randomly in all possible directions in a zigzag manner, and that is called the Brownian movement. This Brownian, so these colloidal particles overcome the force of gravity. They don't settle at the bottom. They are suspended in the dispersion medium. They have a collision with the colloidal particle. So thereby colloidal particles gain energy, moving in a zigzag manner, and that is called the Brownian kinetic property of the colloids. And the interesting property. Okay. Another property is the optical property of the colloids. For optical property, simple example, see the sky appears blue. Why the sky appears blue? Because the nature contains large number of colloidal particles. So light from the sun falling on these colloidal particles. These colloidal particles are sufficiently bigger enough. They will scatter the light rays. The scattered light rays, they got the wavelength of blue light. That's why the sky actually is a space, empty space. Nothing is there, but it appears blue because of the optical property of the large number of colloidal particles in the dispersion medium. Sunlight when it falls, scatter the light rays. The wavelength of the scattered light rays falls into the visible region of the blue light. Thereby the sun appears blue. Means the optical property means these colloidal particles. These colloidal particles, colloidal particles have the property. Sorry, interruption. Correct, what is it? Okay. Welcome back, my dear students. I told I discussed about the kinetic property of the colloid, a Brownian movement. Coming to the optical property of colloids, I have the example of the sky appears blue. Why the sky appears blue? Because the environment is a lot of the particles, dust particles, colloidal particles, so which are of colloidal dimension. Sunlight, they scatter the light rays. They are essentially larger, 10 power minus 6 to minus 9 meter means. The scattering light appears in the wavelength of blue region. That's why the sky appears blue. Even you can observe in your house. So suppose you open the window, sunlight is falling from indoor in your room. You can look at those, the light. Large number of particles can be seen even in the naked eye. But those particles, they are colloidal particles, where you can see in the naked eye because they have scattered the light rays. When you go to the movie, say this is a projector room, to the screen, light is, if you look at the light, large number of particles can be seen even in the naked eye. Because that contains large number of colloidal particles, they scatter the light rays. So those particles are visible even in the naked eye. So that the scattering property of the colloidal particle is the Tyndall effect or the optical property of the colloids that can put in the form of an experiment in the laboratory. Look at this experiment. I have taken the true solution, but it is a crystalline. So this is a colloidal dimension I have taken. This is a colloidal dimension. Two beakers I have taken. One contains the crystallites, like say sodium chloride solution, or obtaining this arsenic sulfide solution or ferric hydroxide salt. So the colloidal solution. You take a light, use a lens to get a convergent beam of light. So this convergent beam of light is passed through this solution. Look here. The same means the path of the light which is not visible in the true solution. Because the particles are too small, they cannot scatter the light. The path of the light is not visible. But here you can see the path of the bright light, you can see the path of the light is visible. So this is the optical property of the colloids. So this the crystallites, the particles are less than 1 nanometer. They are very small. They cannot scatter the light. Those particles have no problem scattering the light rays. But the colloidal particles are sufficiently bigger, 1 to 1000 nanometer, the surface area. They can scatter the light rays. So that thereby they appear in the form of a bright light. This is the optical property of the colloids. So this was demonstrated in the form of a Tyndall effect. I have taken this is the color dispersion is taken. Even you can carry out this experiment in a dark room or you can use an ultra microscope. I have taken out the light source, get one lens or two lenses at a slit to get the convergent beam of light rays. So convergent beam of light rays is made to pass through into a colloidal dispersion. You can see a bright tyndall cone appears in the dark background or when observed through ultramicroscope. So this is the good optical property because of the scattering property. So this is the tyndall cone appears. This cone is called the tyndall cone, and this is the tyndall effect. This is the optical property. The process of scattering the light rays from the surface of the colloidal particle is called the tyndall effect. So because of this the scattering property, the bright tyndall cone appears in the colloidal dispersion. The same property cannot be observed in a true solution. They cannot scatter light rays. Only we can distinguish between a, so look at orally, we cannot say which is colloid and which is the true solution. You put a bad ray, you put the light rays. If the path of the light rays is not visible, is a true solution. If you can see the path of the light ray is a colloidal solution. So you can distinguish between the colloids and the true solution by passing the the tyndall effect. Another important application in industry. So we are using a catalyst. So catalysts they are very costly, like platinum, palladium, rhodium. Catalysts are used. And the reactants in industry, if they contain any the poison molecules or dust particle, they will poison the catalyst. We discussed on the study of catalytic poisons. They will completely poison the catalyst. In the industry, what they do, the reactants are completely purified from all poison molecules, including dust particle. The purities, how they check the purity by tyndall box. They keep on tyndall box. So the lattice is passed. Any still particles are there, we can see the tyndall cone formation. They confirm all the particles, dust particles or poison molecules are removed completely. Then only the reactants are passed over the catalyst. So check the purity of the industrial gases before passing over the catalyst. So this the tyndall property is widely applied. So this is the optical property of the colloids. In the kinetic property, colloidal particles are moved continuously in a zigzag manner. Is a kinetic property. In the optical property, so these colloidal particles have got the property of scattering the light rays from the surface of the colloidal particle is called the optical property. Is called the tyndall effect or tyndall cone. Most important the property is called electrical property of the colloids. Very interesting. Electrical property or is called the electrophoresis. In the electrophoresis, look at a simple experiment. I have taken the U tube. So this is a U tube. You fit two metal electrodes. This is the positive pole of the battery, negative pole of the battery. I placed here the colloidal dispersion. Let us say I have taken arsenic sulfate salt, some salt, colloidal dispersion. Let's say I have taken arsenic sulfate salt. You pass the electric current. What is the observation made here? You can observe here all the particles, colloidal particles in this the dispersion medium found to be moving towards only one of the electrode. Positive plate, negative plate. I take the arsenic sulfate salt. All the particles in the salt is found to be moving towards the positive plate. After reaching the plate, so these particles will get coagulated. So this is observation. So with this, what is the inference we can draw from this experiment? I take the U tube, I place the dispersion medium, and this is the place the two electrodes are passing the electric current. I observed here all the particles of a particular salt are found to be moving towards only one of the electrode. All the particles are moving towards the positive plate, or all the particles may move towards the negative plate. All the particles of a particular salt are found to be moving towards only one of the electrode. And then after reaching the electrode, they will get coagulated. What is the important observation we can observe here? So this is the first observation. Since the colloidal particles are moving in the electric field, what that shows? Colloidal particles are charged particles. See inference. If they are not charged particles, they could not have been migrated in the electric field. They are moving towards the electric field means we can confirm. See, these colloidal particles carry electric charges. And another important observation is all the particles of a particular salt moving towards only one of the electrode. All the particles will go towards the positive plate, or all the particles will move towards the negative plate. What that indicates? That indicates that all the particles of a particular salt carry only one type of charges. They may have a positive charge or they may have a negative charge. You take electrolyte like sodium chloride, that contains both positive and negative ions. Unlike here electrolyte, this colloids, they got only one charge. Suppose if you take the arsenic sulfate salt, the particles are found to be moving towards the positive plate. What that indicates? It indicates that it is negativity. Negativity charged particles are there. So this arsenic sulfate are negatively charged, they move towards the positive place. Suppose we take ferric hydroxide salt. In the ferric hydroxide salt, all the particles are found to be moving towards the negative plate. That shows ferric hydroxide contains the positive charged particle. That is all the particles of a particular salt, they carry only one type of charges. That's why they move only towards one of the electrode. If they move towards the anode, we call it the anophoresis. If they move towards the cathode, they call it the cataphoresis. In general, we call it the electrophoresis. That is so the migration of colloidal particles in the electric field towards one of the electrode is called the electrophoresis. Define electrophoresis. The movement of the colloidal particles in the electric field. So towards one of the electrode is called the electrophoresis. So these particles, after reaching the electrode, they appear, they are coagulated. That indicates if the charges are removed, so these colloidal particles become unstable. Once the precipitation occurs, they become unstable. So that shows that the colloidal particles are reaching the electrode, the coagulation occurs. That shows us that if the charges are removed, the colloidal particles will become unstable and gets coagulated. For three very important observations we can draw by this experiment. This experiment shows colloidal particles carry electric charges. They carry only one type of charge. They may have a positive charge or they may have a negative charge, unlike electrolytes. Electrolyte contains both the charges. But unlike electrolytes, you have only one type of the charges. They may have a positive charge or they may have a negative charge. If the charges are removed, the solid will become unstable and can be coagulated. Look here, this is called electrophoresis. Based on the moment, some of the example I given the positive charged salts and negative charged salts. So this is the positive salts and depending upon the migration, what the direction of the migration in the electric field. So these are the example of the positive salts and negative salts. Because these are the important data you have to remember and you have to memorize. Because the examination, all national examination, he will give the salt, but he will not give the charge. If you can know what is the charge, then only we can answer the question. How to know this charge? You must only memorize this step. Say the example of hydrated metallic oxides. What is alumina, hydrated chromium, hydrated ferric oxide. So metal hydroxide like ferric hydroxide, aluminum hydroxide, chromium hydroxide, calcium hydroxide. But basic dyes like methylene blue, Prussian blue, even hemoglobin blood. But the blood is a positive charge. Because all the particles of a blood go to the most negative plane. That shows they got a positive charge. So based on the direction of the movement in the electric field, some of the important colloids have the positive charges. Among which blood is the most important colloidal system having the positive charge. And even the metal hydroxide, ferric hydroxide, aluminum hydroxide, there are positive charge. When basic dyes like methylene blue and Prussian blue, they are the positive charge. You have to memorize, no other go for multiple choice point of view. For negatively charged colloidal particles, so metallic particles like the copper, silver salt, gold salt, platinum salt, metal salts, they are negatively charged. But metal sulfide like arsenic sulfate, cadmium sulfate, antimony sulfate are negatively charged. Acidic dyes, these are the basic dyes. Acidic dyes like eosin, congorate, they are negatively charged. Well, salts of starch, gum, gelatin, clay, rubber, latex is negatively charged. Charcoal, so carbon particle has got a negative charge. Remember, so the charcoal, smoke contains carbon particle, they are negatively charged. So even the colloidal graphite in water is called the aqueduct. So this is term used. Aqueduct is anyone colloid is all based in the national examination. Company examination, aqueduct is colloidal graphite in water is negatively charged. Oil dye, colloidal graphite in oil is called the oil dye. They are all negatively charged into the colloidal particle. The analytical property of the colloids based on the movement of colloidal particles in the electric field. So some of the important charges have been identified and you have to memorize the data. Okay, now I will stop at this stage. So today I will before what all I have done. I defined what are colloids. So I give the difference between suspension colloids and crystalloids. And again colloids are heterogeneous system disposed based on dispersion. A number of examples has been given like salt, gel, emulsion, aerosols. And again the types of catalysis, further the types of colloids are given the multimolecular colloids, so macromolecular colloids and associated colloids are given. And we give the preparation of colloids, various methods employed, properties. So purification of colloids by dialysis, electrodialysis or ultrafiltration. Then I given the properties of colloids. Coming to the kinetic property is a Brownian movement, and this is the optical property, Tyndall effect, and electrical property by electrophoresis. We can at this juncture we can conclude So the colloidal particle, based on the size. Size is the criteria to classify the substance into colloids. Any particle, solid, liquid or gas, whose particle size varies between 10 to the power minus 6 to minus 9 meter or 1 to 1000 nanometer. So they are called the colloids. So that is these colloids, this is a heterogeneous and a homogeneous system. It is a heterogeneous system. They got these particles of particular dimension has got three types of properties: kinetic property, optical property, and the electrical property. In the next period I will discuss. So these colloidal particles are charged particle. Then what is the origin? How these particles will gain the electric charges? That I will take up in the next period. Till then, thank you. Okay.